Welcome to G Fun Facts Online. Beneath our feet, the Earth is not a solid, stable sphere. It's more like a cracked eggshell, a mosaic of massive tectonic plates that are constantly grinding against each other. These movements, usually too slow for us to feel, build up incredible stress along fractures in the crust called faults. When that stress is suddenly released, the ground shakes. Earthquakes are one of nature's most powerful forces, capable of reshaping landscapes in moments. But for all our scientific knowledge, many of the most dangerous faults remain hidden, buried deep underground, silently accumulating strain. Finding these unseen threats has been one of the greatest challenges in geology. But that's changing. We are in the middle of a technological earthquake of our own, one that is shaking the very foundations of how we study our planet. Artificial intelligence is giving us a new set of eyes, capable of peering into the Earth with unprecedented clarity. Today, we're journeying into the heart of this revolution to see how AI is uncovering thousands of hidden faults and helping us build a safer world on our ever-shifting planet. For centuries, the hunt for geological faults was a story of painstaking detective work. The earliest fault finders were geologists, with little more than a rock hammer, a compass, and a sharp eye. They walked the land, mapping rock formations and searching for telltale signs of a break in the crust. A sudden cliff cutting across the landscape, a stream channel that mysteriously jogs sideways, or a line of springs forced to the surface. All these could be clues pointing to a fault below. This is the bedrock of geology, but it has a major limitation. It only works for what's visible on the surface. Many faults are buried under thick layers of soil, dense forests, or entire cities. To understand a fault's history and its future danger, geologists had to get their hands dirty. The field of paleoseismology involves literally digging into the past. Scientists excavate massive trenches across a suspected fault zone. The walls of these trenches reveal a cross-section of the Earth, like a layer cake of history. They can see layers of sediment that have been broken and shifted by ancient earthquakes. By dating organic material found in these layers, they can build a timeline of seismic events, estimating how often a fault ruptures and how powerful its earthquakes might be. This is crucial information, but trenching is slow, expensive, and gives you a detailed picture of only one single spot. To see deeper and over wider areas, geoscientists developed one of their most powerful tools, the seismic reflection survey. The principle is like a medical ultrasound or a ship's sonar, but for the entire planet. Scientists generate powerful sound waves at the surface using giant thumper trucks on land or compressed air guns at sea. These sound waves travel down into the crust, bounce off different rock layers, and the echoes are recorded by thousands of tiny sensors called geophones. After immense computer processing, this jumble of echoes is transformed into a 3D image of the subsurface. In these seismic images, faults often appear as sharp breaks in the otherwise continuous layers of rock. For decades, interpreting these 3D seismic volumes has been the primary way we've found faults, especially for industries like oil and gas exploration. But all these traditional methods have serious limitations. Interpreting seismic data in particular is a monumentally slow and subjective task. An experienced geoscientist could spend months manually clicking and tracing faults, slice by slice, through a massive 3D data cube. Two different experts looking at the same data might come up with two different fault maps. And with modern surveys generating petabytes of data, that's thousands of trillions of bytes, it's become impossible for humans to analyze it all effectively. Subtle faults, or complex networks of tiny fractures, are easily missed. This is where the AI revolution begins. The same technology that powers facial recognition and self-driving cars is now being turned towards the Earth's crust. At its heart, AI, and especially a type of AI called deep learning, is all about teaching computers to recognize patterns in data. And geology is all about patterns. I can analyze an entire 3D seismic volume at once, identifying subtle relationships and features that are completely invisible to the human eye. The most powerful AI models for this task are called convolutional neural networks, or CNNs. These are the models that have mastered computer vision. A CNN learns to see in stages. First, it recognizes simple things like edges and corners. Then it combines those to see more complex shapes. This is perfectly suited for finding faults. We can treat a 3D seismic volume like a giant 3D photograph. We train the CNN by showing it thousands of examples of seismic images that have been labeled by human experts, saying this is a fault and this is not a fault. The AI learns what a fault looks like in the data. Once trained, it can scan new, unseen data volumes at incredible speed and produce what's called a fault probability volume. Every single point in the data is assigned a score based on how likely it is to be part of a fault. This gives geologists a crystal-clear map of the entire fault network, revealing details they never could have seen before. An even more advanced architecture, called a UNet, takes this a step further. The UNet was originally developed for medical imaging, to do things like perfectly outline a tumor in a medical scan. It's incredibly good at precision. In geology, a UNet can produce a clean, pixel-perfect map of the fault planes themselves, not just a probability cloud. These sophisticated models are delivering results that are more accurate, more detailed, and more geologically consistent than ever before. But of course, an AI model, no matter how smart, is nothing without data to learn from. The primary fuel for these geological AIs is still the massive cubes of 3D seismic data. But what's truly revolutionary is how scientists are now fusing this with other types of data to create a more dynamic picture of the planet. For example, a technique called INSAR uses satellites to monitor tiny changes in the ground surface from space with millimeter-level precision. It can detect the ground slowly bulging or sinking as strain builds up along a hidden fault. There is also LiDAR, where planes or drones fire rapid pulses of laser light at the ground to create an incredibly detailed 3D map of the surface. By digitally filtering out all the trees and buildings, LiDAR can create a bare earth model, revealing subtle fault scarps and other features hidden by vegetation. Add in data from high-precision GPS networks that track the real-time movement of tectonic plates, and you have a symphony of data. AI is the conductor that can make sense of it all, linking the deep structure seen in seismic data with the surface deformation that signals an active and potentially hazardous fault. One of the biggest challenges, however, has been getting enough high-quality, labeled data to train these AIs. Manually labeling faults in terabytes of data is a huge bottleneck. So scientists came up with a clever solution: synthetic data. Using their knowledge of physics and geology, they can program computers to generate a virtually limitless number of artificial, but highly realistic, 3D seismic worlds. These synthetic worlds come with perfectly accurate fault labels already built in. It's like building a flight simulator for a geological AI. The AI can be trained on this enormous perfect dataset to learn the fundamental characteristics of faults before being fine-tuned on smaller sets of real-world data. This is a game changer, breaking our dependency on limited, hand-labeled data. So what has this new technology actually found? The discoveries are stunning. Let's go to Italy, to the Campi Flegrei caldera, a supervolcano just west of Naples where over 500,000 people live. The area is constantly experiencing ground uplift and swarms of small earthquakes. Understanding the faults here is critical. Recently, researchers applied an AI model to the seismic data. The results were revolutionary. The AI identified over 54,000 earthquakes in a 2-year period, a 4-fold increase over the 12,000 detected with old methods. This massive new catalog of quakes allowed scientists to map the underground fault network with unprecedented precision, revealing two previously unknown fault systems converging directly beneath the populated town of Pozzoli. This provides a vital leap forward in understanding the risk to the 500,000 people living there. Or, let's look at Yellowstone National Park in the United States. Researchers used a machine learning algorithm to re-examine 15 years of old seismic data. The AI unearthed approximately 86,000 previously undetected tiny earthquakes, increasing the known seismic activity for that period by a factor of 10. This revealed that more than half of Yellowstone's earthquakes occur in dense swarms, likely caused by hot, pressurized fluids moving through the volcano's plumbing system. It's a much more detailed picture of the processes happening deep beneath the caldera, a task that would have been impossible for humans to do manually. The applications are global. In earthquake-prone nations like Japan and New Zealand, AI is becoming an indispensable tool for mapping soil stability to guide safer construction. In the energy sector, AI is accelerating the search for oil and gas by rapidly identifying fault-bounded traps. More importantly for our future, it's also proving to be a powerful ally in the hunt for geothermal energy. Geothermal reservoirs depend on complex fault networks that allow hot water to circulate, and I can pinpoint the most promising locations for drilling, reducing the high cost and risk of exploration. And when disaster does strike, I can help. In the aftermath of a major earthquake, AI algorithms can automatically analyze satellite and drone imagery to rapidly identify damaged buildings on a citywide scale. This gives first responders an invaluable map of the hardest-hit areas, helping them prioritize search and rescue efforts. For all its power, this new technology isn't without challenges. The very complexity that makes these deep learning models so effective can also make them opaque. This is known as the black box problem. The AI gives you an answer, but you don't know why. In a high-stakes field like earthquake hazard assessment, that's not good enough. This has led to the rise of explainable AI. The goal is to develop techniques that can lift the hood on the AI's brain and show its work. An interpreter can see which features the model was paying attention to, confirming if it's using geologically sound reasoning or if it's being fooled by noise in the data. This builds trust and fosters a collaborative partnership. The goal is not to replace human experts, but to augment them. AI handles the heavy lifting of data analysis, while the human geoscientist provides the critical thinking, context, and geological wisdom that machines lack. The future is even more exciting. The next generation of models are called physics-informed neural networks, or PINNs. These are AIs that are forced to obey the fundamental laws of physics. Their predictions must be consistent with both the data they see and the physical equations that govern how waves travel through the Earth. This makes them more accurate, more reliable, and less dependent on massive training datasets. The ultimate goal is to move from simply mapping faults to monitoring them in near real time. With AI, we are building systems that can continuously ingest and analyze data from thousands of sensors, tracking the subtle signs of strain building up along fault zones. While true earthquake prediction, knowing the exact time, place, and magnitude, remains a distant dream, AI is giving us the tools to move towards a more dynamic and probabilistic form of forecasting and to improve our early warning systems. The ground beneath us is a dynamic and powerful system that we are only just beginning to truly comprehend. For generations, our view into the Earth's depths has been hazy. We were like detectives trying to solve a case with a few smudged fingerprints. Now, artificial intelligence has given us a revolutionary set of forensic tools, allowing us to see the Earth's hidden plumbing with astonishing clarity. From the bellies of supervolcanoes to the search for clean energy, AI is not just redrawing our geological maps, it is giving us a more dynamic and actionable understanding of our planet's hazards. The journey ahead requires a partnership, where the computational power of AI enhances the irreplaceable wisdom of human experts. By embracing this technology, we are not just uncovering hidden faults, We are illuminating a path toward a future where we can live more safely and intelligently on our restless, beautiful, and ever-shifting world.